Hello and welcome to another AP Physics 1 review session. Today we're going to talk about uniform circular motion and the ideas of universal gravitation. A bunch of scary words to say some simple things. First off, we want to define the ideas of uniform circular motion as things spinning at a constant rate. So that means that something spins at a constant rate. The time for it to go around remains constant. So in the ideas here, we're saying spinning around at a constant rate. Notice I'm trying to focus on a big idea, because if it spins at a different rate, then we're then dealing with rotational ideas. So many times we use the words uniform circular motion. When we say uniform circular motion, we're saying it's spinning around at a constant rate. Now, to reference those ideas, we're really talking about the time for it to go around one full time. We call that thing the period. So we've many times shown with capital T to show that idea, and it is indeed the period. Okay, so in this case, we're dealing with a period that is constant. So what do we mean by that? Okay, so if we have a wheel, okay, and that wheel is moving and spinning at some rate, and as long as it spins at the same rate, the time for one point on here for it to go all the way around and back to that point stays the same the whole time. We're talking about uniform circular motion. Now, the big part of this comes into not really looking at like a part on a wheel or something like this. More often it's shown in terms of AP questions as items on strings. Now, if I have an item like this, okay, so it's a ball on a string. We can even say like it's an amusement park ride, and we got riders out here, and there's an arm attached to this thing. This thing's spinning around. Well, as this thing is happening, right, we want to talk about it's going to undergo uniform circular motion. Again, as long as t stays constant. So if that's happening and it's spinning at some rate like this, there are some questions that we can ask ourselves. So let's say this is a ball with a string here. If at some point in time the string was to be cut, which way would it fly off? It's trying to go in a straight line path, so it would try to go that way. So we can even say its velocity is in that direction. As it goes around, it's constantly changing that direction, so that means it is accelerating. What type of acceleration is that? How do we define that? This. AC is equal to b squared over r. Now, in looking at that, AC is b squared over r. We look at this idea and say, okay, it's accelerating if it is indeed changing direction. Now, how do we define the force that's causing that acceleration? Well, centripetal force is equal to mass times the centripetal acceleration. So really, it's mv squared over r. Now look at this relationship. The larger mass the mass that we have spinning, the more force that we're requiring. If this radius increases, we find that force decreases. Well, why? Because ultimately it's going to be spinning at a different rate. We find that if it's spinning faster, exponentially, this would have to increase. So it's spinning twice as fast in terms of how fast it's going about. That means it would have to increase that inward force, that centripetal force. So what I'm trying to reference is, as it's spinning around like this, we have an inward force, we call that centripetal force, as well as the centripetal acceleration directed like this. Yes, if things change and it speeds up, slows down in terms of how it's spinning, that deals with different ideas. In this case, we're just simply dealing with the ideas of uniform circular motion, meaning it's spinning around at a constant rate. Now, we have this velocity being directed like that. It's perpendicular to the inward force. Centripetal literally means center seeking. Now, another way that this could be shown in an AP question is if it's a problem where you have something like this, or it's a roller coaster. And then we saw some different types of questions like this. Say, okay, well, if it goes down like this and it flies around, right, whatever, okay? And we're trying to deal with the forces at that point. Now, if we were to deal with the forces at that point, you may say to yourself, well, they're going through a loop. Shouldn't there be weird stuff going on? Yes, but ultimately we can have to think about two forces acting on those people right there. Think about old ideas in terms of what we just talked about in the last unit in terms of dynamics and forces. Really, at that point, I have Fg pointing that way. Now, for something to undergo circular motion, we need to have a force directed towards the center. So in this case, there needs to be something pushed this way. Centripetal forces don't just happen. They're caused by things. In this case, the thing that's causing that circular motion is the surface itself pushing in on it. What does that mean in this case? We also have a force normal here pushing down. That's why when going through like this, spinning around a roller coaster, you feel kind of resistive because what's going on there is, one, you're trying to go straight, and two, that surface is providing that inward force pushing you back in towards the center of that circle. Now, looking at that, you may say, oh man, that looks kind of crazy. If we're to try to deal with forces here, some of the forces are mass times acceleration. What are the forces? Notice the way in which I've written that. It's a negative force gravity, but picked down to be negative force normal like that. That means I'm going to have to negative acceleration. Does that mean it's accelerating that way? Yes, because it's spinning. As it's spinning, yes, it is indeed changing direction. So we could go ahead and simplify that to some different things, put that stuff in there, define force normal. I can put that in terms of that. That's fine too. Uniform circular motion is basically a highly conceptual idea. Now, we want to focus on another one today, the ideas of universal gravitation. Universal gravitation gets linked with this idea because of how it can be applied. And we'll see that in just a moment. So universal gravitation shows something kind of cool. So it's saying that F is equal to G, M1, M2 all over R squared. This is the gravitational force. That's a constant. That's just the constant and it stays the same. 6.11 times 10 to the negative 11. Okay, that's mass 1, that's mass 2, and that's the distance between those two masses. Okay, so this deals with the relative attractive force. Notice, this deals with M1 and M2. Those forces on both are the same. Third law states action-reaction forces. So the pull on this one is the same as the pull on this one. These two things get pulled together. Now, this holds true with any type of anything that has mass within the universe, as well as large bodies. We see it present a lot more with large planets. But the thing that we want to talk about here on Earth is, on Earth, all of that stuff turns into 9/8. That's why we get mg, right? Because that's g. Now, the other part we want to look at is what happens in terms of the forces, in terms of relationship. Now, if I'm dealing with those forces, and if we deal with those masses, you realize that that was the double, that would double. That was the double, that would double. If both these double, that would quadruple. The weird thing happens with the radius. Now, if we take a look at this, dealing with force versus radius, you should realize, or the distance between them. Okay? As we increase the distance between them, we should realize that the force between them decreases. It doesn't decrease proportionally, it decreases exponentially. So what would this graph look like? Something like that. Now, this is weird to think about. That means that no matter what's going on, right, we have very large forces when things get very close to each other, and we get very small forces when things get very far. But that, if you notice this still is exhibited here, and it's still exhibited here. That means that that pull is still evident when, or is really close when those things are very much near each other. But as you get farther away, it weakens, but you can never escape it. So that means that every particle in the universe is ultimately pulling on you right now. The things that are even like light years away are still pulling on you. It's still a very, 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 very small amount, and proportional to that distance squared. And it's an exponential amount. Now, why do we talk about these two ideas in the same unit? Well, it's because of satellites. So if we have the Earth, and we have a satellite orbiting it, and that satellite's going around like this. Okay? We could say it's something called a synchronous satellite if it has the same rotation as the Earth. We could do some stuff with that. But in this case, we're just saying it's just a satellite that's orbiting around the Earth. Now, as it's orbiting around the Earth, it's not falling into the Earth, it's falling around. Now, how does that happen? Because it has such a large speed this way, but it's accelerating this way. Now, what would cause it to have a large acceleration this way? Well, universal gravitation, the gravitational force between it and the object. Now, it needs to be launched at a very large speed so that acceleration allows it to spin about. So in this case, say to yourself, okay, if I was to analyze the forces, so some of the forces in this case are equal to mass times acceleration. Well, I know that it's going to have centripetal acceleration, right? That's v squared r. Well, what type of force is acting on it? The only force we have acting on this thing is F. And I'm going to put capital G to denote something a little bit different than we're used to. Now, that F, capital G in this case, is not mg. It is not mg. The reason for that is because we're not dealing on the surface of Earth, rather we're dealing with some distance out. So that means I can make this. So I get G, M. Now, I've got a bunch of M's now, so let's call this Earth and let's call this S. Okay, S for satellite, E for Earth. So mass satellite, mass of the Earth all over r squared, cool, and is equal to, well, that's the thing, it's accelerating. The Earth is not accelerating. We're talking in terms of this reference frame. The satellite is accelerating, so it's ms AC. Notice that looks all kinds of messy, but first off, I should notice that that mass s cancels out. Okay, so GME all over r squared is equal, okay, that's b squared over r. Cool. Oh, hey, if I look at this, I find that one of the r's also cancel out. That falls out as well. So GME all over r, root of that is equal to v. So that means that the speed of a satellite as it goes about any type of celestial object, so it goes ahead and orbits it. Well, it doesn't just work for Earth. You could do this for mass of a person relative to their distance out. Granted, you should realize that it's going to have to be very, 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 very large velocity in order for that stuff to happen, because those have small relative masses. Now, the AP question that we want to focus on this video deals with the relative density and how that mass changes some stuff. So one thing they could say is, they could say planet Y has 1g, right? And we say planet 2, or planet X, experiences 2g. Okay? If we're saying they have the same size, compare the density. Or there's some type of phrasing of this question. Okay? Say, well, how do I relate the ideas of density in this? Well, F is equal to G M1 M2 all over R squared. We should realize that only this stuff would affect that gravitational pull, that gravitational acceleration. So really, I could say that would be little g. Now, how can I relate this idea of density? Well, density is equal to M over V, right? Well, but density doesn't deal with just straight line stuff. It has to deal with density of a celestial object. It's going to deal with density or volume of a sphere. In this case, it's 4/3 pi r cubed. Now, in looking at that idea, see, that looks kind of ugly as I show it there. Now, in looking at what I have here and what I have here, you should say, man, that looks kind of really, really ugly to show this thing. But if I go ahead and I'm saying, okay, I want that to be little g, right? I want to try to put this in terms of this. Now, how can I do that? How can I do that? Well, I can do it by trying to modify it to make this thing here. So if I multiply the top and the bottom by 4/3, and that's g, and I divide by r, and I multiply by r. Okay, so this was all my original stuff, okay, to compare these ideas. Excuse me, and I need to divide by pi and multiply by pi. Okay, now, in doing that, you say, okay, doesn't that look all kinds of weird and ugly as I just did that? But I just went ahead and I rewrote it in terms of my original conditions, and I rewrote it so I can go ahead and make this thing rho in terms of the density. So it's m 4/3 pi r cubed. So this is rho. So that means I can write this 4/3 g r mu rho is equal to g. Now, what do I mean by that? Notice what I just did there. I put in terms of density, in terms of small g, in terms of what's going on here. So that means if this thing is twice that, we can throw it twice in there to show the relative density between the two different ideas. Now this is definitely more, like there's only a couple questions that I can say this is kind of a guaranteed type of problem that you would see in some of these ideas. This is one of those kind of guaranteed type problems. As always, thanks for watching. I'll catch you on the next video.